Okay, so just a heads up, I'm going to take attendance, but at the end of class. Okay, so probably around 9:40ish, 9:45. I'll pass this paper around, and you have to sign in. Okay, and I take it at the end of class just because I know students will show up for the quiz at the beginning of class, but a lot of times they leave, and so I want to give you credit for staying through to the end. If you're watching this on YouTube and you were not here in class, you will miss signing the paper, okay? And I keep these things, okay? And you have to write your name on here, and I'll keep these. And so if anybody says I didn't give you credit for attendance, I'll say, well, if your name's not on this paper, that's why you didn't get credit for it, okay? So I'll pass this around at the end of class, and then I'll just kind of count the number of heads I see, number of faces I see, and the number of names that appear on here, just to make sure there's a match. So do that, okay? All right, so we'll finish off chapter 4. Oh yes, and then for during office hours, I forgot to bring my stack of quizzes, and so if just this week, if you want to take a look at your quiz from last week, I'll let you do that after class. Normally, I don't do that, and I just say come before class, and you can take a look at your quiz, but I'd forgotten the stack of quizzes. So if you want to take a look at your quiz from last week, you can stay after class today and take a look. But normally, if you want to look at your previous week's quiz, come before class and then come ask me. Okay. Okay, so we will continue on. So now we are moving into modeling linear trends. And so this involves creating an equation of a line to summarize the relationship between x and y. Okay, so here we create the equation of a line to summarize between x and y. Okay. And so if you think back to your days in algebra, and you learned about writing the equation of a line. Okay, so in algebra, how would you give the equation of a straight line to me in algebra? You'd say y equals mx plus b, right? This is kind of what we've heard. And what does m represent? Slope, and b represents the intercept. Okay. In statistics, we also have a slope and intercept, but we, I don't know, have confusingly changed the letters. Not on purpose, but just, well, I understand the reasons why they use these letters in statistics. But in statistics, we have a slope and intercept, but the equation is y hat, okay, is equal to a, and a is now our intercept, plus b times x, and b is our slope. Okay, and the hat over the y signifies our prediction for y. Okay. So the way, so we'll work through the example that the book provides, which is what they have done is they have gone through and looked at a whole bunch of different books, okay? And what they did is they measured how thick is this book, okay? And they also flipped to the last page and counted, or saw how many pages were in the book. Okay, so you know, maybe the book is, you know, if we used our textbook, you know, my textbook says it's got an index here, so my number is not going to be quite right, but you know, it's got something like 700, so maybe close to 800 pages, and I'm measuring the width in millimeters, and so I don't know. I don't know what millimeters look like, so maybe this is like 28 millimeters thick or something, right? It looks like it's a little over an inch. So I would have a mark here for you know, 800 pages and 28 millimeters thick. Okay, and so imagine us gathering a bunch of data. We go through a whole bunch of textbooks, or not even textbooks, just books in general. We count how many pages there are, and and we measure the width of the book. Okay, so our data table is, you know, we have the book, and for X we've got number of pages, okay, and width in millimeters. Okay, and so, you know, book 1, whatever it is, maybe there's I'm going to just make up a number, 790 pages, and it's 28 millimeters thick or something like that. Okay, and then maybe there's another book, it's got 200 pages, and it is, I don't know, 12 millimeters thick. Okay, I'm just making stuff up. All right, maybe we have a book that is 340 pages and is 18 millimeters thick or something like this. Okay, and we want to create, okay, we desire to make an equation that summarizes the relationship between the number of pages and the width of the book. Okay, and so what we can do, okay, in this form of our prediction, we can say the predicted width is equal to 6.22 plus 0.0366 times the pages. Okay, and so this is the output, or this is what the book provides for us as an equation that summarizes the relationship between the number of pages in a book and its predicted width. Okay, and so we'll take a look at this in further detail to see kind of how this thing works. Okay. Okay, and so you know, I'm just gonna pretend to draw some dots here. I guess I'm not pretending, I am actually drawing these dots. But I'm going to pretend like they're accurate. Okay, and oops. So the trend line, this is supposed to be a straight line. This is what happens if you graphed this, okay? And so on our x-axis, we have pages, okay? And on our y-axis is the width. And this red line is our trend line, which is predicted width is equal to 6.22 plus 0.0366 times pages, okay? So if we use our prediction line, okay, so using our prediction line, Okay, we can make predictions for a particular book. Okay, so using our prediction line, if a book has 500 pages in it, okay, then we would plug that in. Okay, we would predict that its width is ... We're going to do, so I'm going to just plug this in. We're going to have predicted width is equal to 6.22 plus 0.0366 times, we're going to plug in this number 500 for pages, okay? All right, and so over here, I got to, so I do, I can just type this in, 6.22 plus 0.0366 times 500, and it says 24.52. So this is my predicted width, okay? We predict that its width is 24.52 millimeters. Okay, so if we, so I don't know if that's actually the case. All right, this is our prediction. All right, the book will not necessarily be this exact width, but based on the data that we have and the trend line that exists, our prediction is for a 500-page book, we predict that it would be 24.52. Okay, so keep in mind this is just a prediction based on our data and trend line. Okay, a book with 500 pages may actually be wider than 24.52 millimeters, or less wide, narrower. Okay, so this is just a prediction. Okay, all right. This this trend line, it's often called the regression line, and what it is it is the quote best fit line. It is the line that reduces the distance. So this trend line will not fit our data points exactly, right? Because our data has scatter. Okay, so the only time the trend line fits our data perfectly is if there is no scatter in our data. But if there's any scatter, it's not going to fit perfectly, right? So it's gonna probably go through, kind of the middle of all of these points, or whatever, this idea of middle that we have. And the line, okay, so some smart people did calculus and it did a bunch of work. It is the line that minimizes, if I've got a dot out here, it minimizes the distance, the vertical distance between each data point. So every single one of these dots, it calculates, the distance from the dot and the trend line, and these distances, they're known as residuals. Okay, it minimizes the square of all of these residuals. So you take each of these vertical distances and you square all of these distances. The line that makes the smallest total square of all of those distances is our trend line. Do you have to worry about figuring all of that? I'm not going to make you worry about that, okay? But if you're curious, how do we know this is the best fit line? It is the line that minimizes the square of our residuals, okay? So just I guess FYI, if you want to know, okay, the regression line is the line that minimizes the total sum of the squared residuals. Okay, and the residuals are equal to the actual value minus the predicted value. Okay, it is. It's probably good to know that a positive residual means your actual value was larger than what we predicted, and a negative residual means the actual value was smaller than what we predicted. That's, I think that's a good thing to know. So I'll write that. Okay, so a positive okay. So far, so good. Okay, so to find the regression line, okay, the slope B is equal to R times SY over SX, okay? And the intercept A is equal to BX bar minus Y bar. No, I'm sorry, I have this backwards. I apologize. It's Y bar minus BX bar. I have those two things mixed up. Okay, all right, so basically from your data, you will need the following 5 numeric summaries or summary statistics. Okay, and what are they? They are X bar. What does X bar represent? The mean of our x's. Okay, so it's the sample mean of x. Okay. What does S represent? Standard deviation. Okay, and so Sx is the sample standard deviation or standard deviation of x. Okay, so Y bar would then be the mean of y. And what would Sy be? Standard deviation of y. Okay, so we know how to calculate the mean of x, right? If I gave you a bunch of values and I said these are x, you know how to calculate the mean of x. Okay, and if I gave you a bunch of x, you could also get the standard deviation of x. Okay, it'd probably be tedious if you had like 30 numbers. Okay, we probably don't. I would not do that to you guys. But if you had to, you could, right? If somebody says, I'll give you $500 to do this, you would try really hard to do it right, okay? Okay, so we know how to calculate all of these. And then the last one we need is R, which is what? correlation, right? In correlation, we said we're not going to learn how to calculate in this class. This will be, you know, calculated with the computer. Okay, so you know you have these 5 numbers, and all you do is you just plug those numbers where they belong, and you'll get a b. Once you get the b, the slope, you're going to plug y bar and x bar and b together, and you get a. Okay, and then you put these together, you combine a and b to get predicted y, or y hat, is equal to a plus bx, okay? And this is the equation of our regression line. Okay, which we can use to make predictions. All right, is that okay? All right, and so, you know, we got, I think you've got some homework exercises that go through this. I want to focus on the interpretation, okay? So we're going to focus on interpreting the slope and also focusing on interpreting the intercept. All right, so what does the slope mean? And don't say rise over run, because I would ask you, what does rise over run mean? Which I probably just get the slope. All right, so let's talk about this, right? So we have y hat is equal to a plus bx. Okay, so this is our intercept, and this is our slope. All right, let me bring this over. All right. Let me just drag this over here. Okay, and so the intercept here is 6.22. Our slope here is this, and our x is actually pages and y is our predicted width. Okay, so the y variable is what we are predicting. Okay, the x is what we are plugging in. Okay, so our x variable, this is known as our independent variable. This is also known as our predictor variable. Okay, this is the variable we are using to make a prediction. Okay, we use this variable to make the prediction. The other, so in our cases, we are using the number of pages to predict how wide the book is. Okay? We could have set the whole thing up differently, right? We could have played the opposite game where I give you the width of the book and you try to tell me how many pages are in the book, okay? But that's not how we set it up. So how you set it up matters, okay? You could, if you wanted to, set it up the other way, but in our case, we have set it up so that we are using the number of pages in a book to make a prediction about the width of a book, okay? So we chose to use the number of pages in the book to make a prediction about its width. Okay, and so what that means is that in the scatter plot, the x variable pages always shows up down here, and then the y variable width shows up over there, okay, in your data looks something like that. Okay, and then so over here, y would be called our dependent variable. Or our response variable. Or the predicted variable. I'm sorry, I forgot one thing over here. Explanatory variable. Okay. All right, and this is the variable we are making predictions. This is the variable we're predicting, basically, okay? Okay, and so, different people can look at the same data and choose to have assigned the x and y differently, but that's going to change the resulting equation and whatnot. But however, whatever you have decided, you got to stick with that and use that to for the interpretations. Okay. This, the prediction line, this is, it's also sometimes called the mean line, okay? Which is kind of the, we plugged in 500 pages and we got something like 24.52, I forget, what was it? Yeah, 24.52, all right? Of course, when we actually get a book that's 500 pages, it will not necessarily be 24.52. But if we took a whole bunch of books that were 500 pages, okay, and we took the average width of all of these, that average width should be something very close to 24.52. Okay, so that's what, when we're talking about the prediction, the predicted width, that's what we're getting at, okay? All right, so, our predicted value is, not necessarily, or is not, the actual value of anything. Okay, so for 500 pages, we predict the width is 24.52 millimeters. Okay, if we actually find and measure a 500-page book, we will not necessarily get okay. But if we find many 500-page books and take the average, that average should be very close to 24.52. I'm gonna run out of space. Okay. Let me guys finish copying that down. Okay. Is that all right? So next slide. Okay, so let's talk about each of these things. The 6.22 is our intercept, and our slope is 0.0366. Okay, so let's talk about what the slope means. Okay, so the slope is 0.0366. Okay, what does this mean? All right. The slope is how much we expect y to change if x increases by 1. Okay? So in our case, what is y? Y is the width of a book. Okay? So, and what is x? X is the number of pages. So if we add 1 page to a book, how much do we expect the width of the book to change? We would expect that width to not change by very much, right? Adding 1 page is not going to dramatically change the width of your book, okay? And that's why our slope is so tiny here, okay? So this is, so just a reminder, x is number of pages, y is width. So what the slope means, okay? Slope says if we increase the number of pages in a book by 1, okay, we predict that the width of the book will increase by 0.0366 millimeters. That's what we're saying, okay? Which makes sense because each page is very, very thin. So, so the small slope, okay, small slope basically says each page is very thin. Okay, and in fact, adding 1 page, I don't know if you can actually just add 1 page because each sheet is 2 pages, right? So, so basically, it probably says some, if, I don't know how many. 1 divided by 0.0366 is 27. So, basically says like there's about 24 sheets of paper in a millimeter or something like that. 23, 24 sheets of paper in a millimeter. So about 27 pages per millimeter, something around there, okay? That's what our slope says. Okay, and then let's talk about the intercept, okay? The intercept, so write all of this down and then I'll give you, I guess, some other things that we can try to interpret the slope and intercept, okay? The intercept is what? 6.22. What the intercept is our prediction for y if x is 0. Okay? Sometimes it does not make sense to have x equal to 0, and in those cases, the interpretation of the intercept won't make sense. But sometimes it makes sense to have an x equal to 0. Okay? So sometimes it does not make sense in those cases, the intercept will not have an interpretation that makes sense. Okay, but in our case, it says if a book has 0 pages in it, we're predicting its width to be 6.22 millimeters. Okay, so this says okay. So, you know, as far as, you know, what does that kind of mean? That kind of means how thick are the covers, right? So if you take out all the pages in the book, how wide is your book? 6.22 millimeters, that's basically how wide are the covers of the book by themselves without any pages. And so in that case, it kind of makes sense. But sometimes you'll have a situation where the it doesn't make sense to have 0 for x. Okay? Is that all right? Okay, so let's just try another one. Okay, so we are looking at some drag racing times. Okay, so this is drag race times. So, you know, these are race cars. And what we are doing is we are measuring how fast they clocked the car to be driving, and how, you know, their finish time. Okay, so so our data looks something like this. Okay, and so this is the speed in miles per hour. This is, I guess, the fastest speed of the car, right? So, you know, when the car starts, it starts off as 0, and then as it goes through the race, it speeds up. So you know, they got a radar gun, and they're measuring how fast. So, you know, they say, you know, how fast did the car go? Okay, and what was its finish time? Okay, in seconds. So, you know, these are very, very, very fast cars. I don't know, how far did they drive? Quarter mile? Less? I don't know. All right, so the prediction line is finish time is equal to 7.84 minus 0.0094 times, I'm just going to write speed, okay? All right, so what is our x variable? What is our y variable? So see if you can identify all these. Don't shout out your answers, okay? Identify the slope, and see if you can write an interpretation of the slope yourself. Okay, and then the intercept, and see if you can write an interpretation of the intercept. Okay, see if you guys can do that. Okay, and so at this time I'm going to go ahead and I'll pass this attendance sign-in sheet around. So just write, so number it 1 through whatever, however many there are of you, and write your name. Print your name nice and clearly. Okay, so I'll write that. Please print. Okay. If you're watching on YouTube, I'm actually going to pause the video here just while students are writing their answers. And I advise you to do the same just because there's going to be some dead time here. All right, we'll see. We'll see. All right, our x variable, what is it? Speed. Okay. Speed of the car in miles per hour. Okay. What's our y variable? The finish time in seconds. Okay, what's our slope? Yeah, negative 0.0094. So don't forget to include the negative there. It's very important. Okay, and what's the interpretation of the slope? Excellent, excellent. Okay, so if you guys didn't hear that, it is if the fastest speed is it goes up by 1 mile per hour. Okay, so if fastest speed goes up 1 mile per hour, right? So this is increasing x by 1. If we increase x by 1, okay, if fastest speed goes up 1 mile per hour, we predict the finish time to go down 0.0094 seconds. Okay? So, these are cars that are, crossing the finish line at something like 300 miles per hour or something like that, 330 miles per hour. So yeah, adding 1 mile per hour is not going to make a huge difference in terms of the actual clock time, but in terms of, finishing first and second place, it might make a huge difference, right? So your finish time is going to go down just a tiny bit. So this is, it's going down. All right, and don't forget to include the word predict, okay? All right, and the intercept is what? 7.84, and what does this mean? So in this case, our interpretation will not make sense because it does not make sense to have a speed of 0 miles per hour. A speed of 0 miles per hour means your car is not moving, okay? So in this case, this, will not, I'm going to just write, will not make sense. Because it says, if the fastest speed is 0, okay, we predict the finish time is 7.84 seconds, okay? Which does not make sense, right? If your fastest speed is 0 miles per hour, your finish time is never, right? If your fastest speed is 1 mile per hour, maybe you'll finish in an hour or whatever it is, right? Or 15 seconds, however it is. So this does not make sense, okay? So it will not make sense because 0 means stopped. Okay. So, make sure you understand this example. I've got a similar example in the practice quiz, and you'll definitely see something like this on next week's quiz where you're going to be given something and I'm going to ask you to interpret the slope and intercept. Lucky for you, it's multiple choice, so so you don't have to formulate all of these things. I used to have it free response, but then there's something disheartening about reading like 50 answers that are just not quite there. So 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 anyway, so it's multiple choice, and that has raised my spirits since. But okay. So anyway, make sure you can do that. I could have asked you, if the fastest speed was 300 miles per hour, what is our predicted finish time? I forgot to put that there, but you could do it, right? You would just plug in the speed and get your answer. Yes?
So if the fastest speed goes up 1 mile per hour, how does the finish time go down?
Right, so if somebody is going faster, will it take them longer or less time to finish the race? It takes less time, right? So if you're going faster, if your speed goes up, the amount of time it takes you to finish the race goes down. So that's why it's going down, okay? So yeah, it's good to always kind of ask yourself, does this even make sense, right? Does it make sense that I'm getting a negative slope? So you have to ask yourself, what does it mean to have a higher speed? It means you're running faster, driving faster. What does it mean to have a finish time that is smaller? That means you took less time to finish, and that makes sense. If you're going faster, it will take you less time to finish the race. Okay, so so the last part, is that sign-in sheet still making its way around? Has everyone signed it? Who hasn't signed it? Okay, so this side hasn't signed it, and that side hasn't signed it. Okay, so we'll make sure all of you guys sign it before you leave today. And don't sign in your friends, okay? Just sign your own, because I've counted how many there are of you here. Okay, so there are a few things to just, I guess, warnings, all right? Warnings and things not to do. Okay, so do not try to fit a linear model. So linear model is basically this straight line, y equals a plus bx, okay? If the data does not look like a straight line, okay? If the data is nonlinear. Okay. Do not the other one, yeah, as always, correlation is not causation. Okay. Beware of outliers. So we've already covered a lot of this stuff, okay? But the topic about outliers, they can really mess things up, okay? So what do you do? How do we handle outliers? Okay, two analyses, one with the outlier, one without. Or, if you find out the outlier is a typo, just throw it away. That's fine, okay? But only if it's a typo. You shouldn't just throw away outliers just because it's inconvenient. You're just like, I don't really like the fact that, I don't know, Hawaii always shows up as an outlier in my analysis, so I'm going to pretend like they don't exist. That's not right, okay? So do two analyses, okay? So okay. The other, okay, and then the last one is watch out, or do not make predictions outside of the range where you've collected data. Okay, And so, you know, this we can just say, do not extrapolate. And I'll give you an example here. All right. Let's say you have a child and you are very excited about measuring his or her height all the time, okay? And so, you know, you measure the height of your child maybe 3 times a year or 4 times a year from as soon as it can stand up, or, so we'll just say he, okay? As soon as he can stand up until he's 10 years old, okay? So let's say starting at age 1, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? And you're measuring 4 times a year, and so you're getting lots and lots of data points, okay? Or you got 40 of these. And then let's say every single time you measure, he grows, all right? Something like this, okay? So ages 1 through 10, he's consistently growing, all right? So this is the height, all right? So then you're like, oh, this is amazing. You know, I get this this formula here, so by the time he's going to be breaking world records when he's 40 years old, okay? Because, you know, he's on this trajectory. So in 30 years, he's going to be the tallest man in the world, okay? Is that silly to do? Okay, we obviously know that's a silly thing to do, because we know people grow, and then around, you know, after puberty, you know, something around, you know, people don't really grow past, I don't know, 20 years old, right? And, you know, once you're around 20 years old, your height's set, right? Some of you reached your peak height when you were like 13, and others of you took a little bit longer. But human growth, you know, you keep growing until a certain age, and then you stop. Okay, so it'd be very silly to say, oh, at age 40, he's going to be the tallest person in the world, okay? But do people do stuff like this all the time? Yeah, people try to predict the future, okay? And this is the clear violation of this do not extrapolate. You know, they'll say, oh, for the past 30 years, you know, this worrying trend has happened every single year, okay? And so by the year 2050, you know, whatever, the world's going to look like this, okay? And it could be good things or bad things. And the thing is we don't know what the future holds, okay? And, you know, it doesn't even have to be malicious. It could just be, you know, the future could look like this. The future could look like this. We don't know. We don't know what's going to happen, okay? So outside of where you've collected data, all of your predictions break down. We have no idea what happens. So linear regression is really just useful for the area where you've collected data. So, you know, and it's unfortunate because it seems a little bit boring then. It's like, you can only do this to say, oh, well, I missed his, I forgot to get a measurement when he turned 7 years old. You know, I knew how tall he was when he was 6.5, and I knew how tall he was when he was 7.5, but on his 7th birthday, I forgot to measure his height. You can use this to make a very good prediction, okay? But as far as predicting outside of the range, it cannot be done. Okay. You guys have not signed it? Okay, so I'm so sorry. Just please come forward and sign this paper here before you leave, okay? And then